Before going any further, I would like to introduce the idea of moment of inertia. Later we'll come back and have a separate video where we calculate it in detail, but I think it's helpful to spend a little bit of time thinking about it before we start trying to use it in equations. The idea of moment of inertia is that it's the rotational equivalent of mass. Again, one way to think about rotation is that we're taking our linear variables, our linear equations, and we're finding equivalents in rotation. And so moment of inertia is actually the equivalent of mass. This moment of inertia is describing how mass is distributed around an axis. And it does depend on what your axis is. Frequently we talk about center of mass as being the axis, but it's not always the case. So it's how the mass is distributed for our size, for our shape. So not just how much mass is there, but where is the mass. The units are kilograms meters squared. So not just kilograms, but also multiplied by meters squared. So that's how you also know that it depends on distance. The symbol is capital I. Make sure, I'm not sure what else you might use for this. It's definitely not M. It's capital I. Some books might call it inertia by itself, but that's a little bit weird since we talk about inertia as linear inertia, like mass as well. Sometimes it gets called moment by itself, but I'll try to always refer to it as moment of inertia, and we always use capital I. The meaning here, to get a feeling, is that the bigger the moment of inertia, the harder the object is to rotate or to cause to rotate. And again, this is just like mass, that I know I can push an object, and if it's easy to push an object, if it's easy to make an object start moving, it has little mass. It's difficult to say push an elephant because it has big mass. Similarly, an object with small moments of inertia is easy to make spin if it initially was not spinning. If it has a very large moment of inertia, it is harder to make spin. So what this looks like then is we need to define our axis. We do care how much mass there is, but we really depend on where it is. So let's think about, say, lead. So some lead that we're distributing over some styrofoam. So in this case, that lighter color we don't care about, it's really, really light, but that darker color is really, really heavy. Now, in these two pictures, there could actually be the same amount of lead. That means that the mass itself could be the same, right? So moment of inertia does not only depend on mass. But if you put all of that lead right at the axis, it's pretty easy to spin. But once you put it around the rim, it's much harder to spin. So this is what we're talking about when we're talking about moment of inertia. So in this case, we do care about what the mass is, but we really care about where it is, the distance from the axis, which in this scenario would be radius, and so we must have defined the axis. When we go to calculate it, we can calculate it either in a discrete scenario or in a continuous scenario. Now, in the discrete scenario, we are again summing up every individual mass, and then we're considering the distance that mass is from the axis, which is r, and that's squared. So the form that you are always going to see for moment of inertia is a mass times some sort of length or distance squared. In the case where you have a continuous distribution of mass, it's now actually your differential mass weighted by the radius, the distance it is from the axis, squared, and then we do an integral. Now, the good news is that you will be using moment of inertia a lot this chapter, but you don't actually have to use one of these first two options in many situations. You can look at what object you have, and you can model it as a shape with a known moment of inertia. There is a table in the book with moment of inertia for many shapes. I'm about to show it, and it's also on the equation sheet. But the modeling step is to say, well, I'm going to take this wheel, and I'm going to say that this wheel is basically a cylinder, or it's basically a ring, whatever you think it is. So you usually can just use a value that's provided to you, but you must be doing that modeling very explicitly. So let's look at the first part of the table. This is distributed over 2 slides. We have 4 objects here. Each one is showing you a picture of what it looks like, how you would describe it, and then what the moment of inertia is. And note that again, in each case, it's a mass, and in this case, a length squared, and then a radius squared, and all you're changing is the coefficient out front. So really, this is about calculating that coefficient out front. Now, this is for a rod. Now here it's shown it as being rectangular in cross-section, but it doesn't matter. Note that the only thing that appears here is the total mass and then its length. So we're assuming that the cross-section, whether it's circular or rectangular, is very small compared to L. And we then have a different moment of inertia if that's not the case. We also have a different moment of inertia if your axis is through the center versus at the end. So notice that your coefficient shifts. So then a second category is a cylinder or a cylindrical hoop. So you would see this called a hoop or a ring. In both of these cases, the radius is through the center. So the cylinder is filled in while the hoop is empty. And we assume that this distance here, the thickness of the hoop, is so small that we can treat it as 0. So again, there's modeling in these three. In particular, we're assuming one distance is very, very small compared to the others. Note here that this is mr squared where this is 1/2 mr squared. Don't think about these as having the constant density. They don't. They have the same mass. So in this case, you have a lot of mass that's much further from the axis, where here you have the same total mass, but more of it's closer to the axis. So the bigger moment of inertia is harder to turn, which is when all of that mass is farther from the axis. So now, two more scenarios with variations. One is when you have a plane or a slab. In this case now, we have something that is rectangular, it's two-dimensional. Note that we're again saying the thickness here is so small that we don't need to worry about it. And in this case, we again have the version where it's through the center and a version where it's through the end. Note that in both of these, the distance B does not matter. However, the distance A does. So do think about this, that this is what you get if you can't just say that it's a thin rod, but this is what you might use if it's, say, a textbook. Now then, another set of scenarios are for spheres. Again, we have a solid sphere, and we have a shell, a spherical shell, or a hollow sphere. Again, in this case, we're assuming that the thickness of the shell is so small we can consider it to be 0. And now look at these coefficients. You have 2/5 and 2/3. Which one's bigger? 2/3. So in the shell case, more of your mass is farther from your axis compared to your solid sphere. So again, this one has a larger moment of inertia, it's harder to rotate. Also, keep in mind that there's a spherical symmetry here. Like, it shows the axis this way, but you can imagine the axis being up and down, and it looks exactly the same. So this table is in your book, and this table is reproduced on the equation sheet. And so if you're trying to think about an object that you think can be modeled as one of these, it is absolutely fair game to use it, though we will go through in a little bit how to calculate it by hand.